Welcome you all to the video lecture of Introduction of Electrical and Electronic Engineering. So here in this video lecture we are going to see over the continuation part regarding to the AC fundamentals. So in the previous video lectures we have gone through regarding to the AC terminologies, law of EMI and the generation of the single phase alternating EMF. So now here we are going to see about to the two topics is the remaining in the AC fundamentals, RMS and the average value of the AC. So the root mean square and the average value of AC we are going to get discussed over here. So here this comes under to the course outcomes CO number 1. So analysis of the basic laws and the simplification techniques is under the electric circuits. Okay, so now we are going to see the definition regarding to the RMS, root mean square. So here this root mean square we can able to get simplifying this basic definition mentioned over here is, let us simply consider this term. So here the amount of alternating current whenever it is needed to produce the same amount of the energy. Here the energy may be of a heat energy, let us consider. So to produces the same amount of what, the heat energy as produced with respect to the direct current, DC current, when it is applied in the the same circuit for a same duration. Here the duration will be till in the terms to the T. So which means that the amount of here I am mentioning here the amount of AC needed to what, produce the same amount of heat energy. So here the energy is in the term of heat energy as produced by what, which term? So DC current as produced by the DC when it is applied in the same circuit with respect to the same duration. So here this duration tells to term of T. So here the above definition is also said regarding to the same explanation mentioned over here. Here they have mentioned that this RMS value with respect to the AC is explained by the what, steady value of a DC current. So this is the simplest and meaningful terms with respect to the above mentioned term. So the amount of AC needed to produces the same amount of heat energy as produced by the direct current with same duration with respect to the time. Now we are going to get determined over this RMS value for any alternating current. Okay, so these two figures as here, these let us consider these two figures, one non-sinusoidal wave and the another one is the sinusoidal wave. Okay, now we are going to consider over with respect to the above figures in the next slide for determining the RMS value for an AC circuit. Let us divide the time base into n terms with respect to the small intervals. So here the 0 to 5 is the time period. Here 0 to t is the time period. It get be divided into n terms like this. So like this they have get divided into n terms. Let us for an duration for the each interval will be equal to the term t divided by n. Here the t is the time, n is the number of subdivisions with respect to the seconds. Now let us we are going to consider over to for each n terms as it will be get denoted to the I1, I2, I3 till IN. So these I1, I2, I3 till IN will be the mid ordinates and these are represented with respect to the currents, which means that the current value for the short time interval. So these intervals can be mentioned with respect to the current I for the short intervals. Now with respect to the here in that definition itself I have said the energy is produced here is a heat energy. So in order to get produce over this heat for the first interval will be obtained with respect to the 0.2 into 10 to the power minus 3 into I1 square RT by N. Here R is the resistance, T is the time period, and is the number of intervals. So for the first interval I am going to get over to get produce with respect to the this terms. Here this current can be applied to the circuit with resistance of R ohms. So actually the total heat produces will be will be obtained with respect to that of the first interval time, second and the last interval time, which means that I1 to In. So finally the total heat, which means that the total heat produced will be equal to that of sum of heat produced in n intervals. So this 0.24 into 10 to the power minus 3 into the I terms, small interval terms, is RT into I1 square plus I2 square till In square divided by n. How many number of intervals is in the wave, half wave. So this is the RMS value. So here this I term will be equal to that of the square root of the mean root RMS value. So root of the mean value, square root of the mean value of the sum of the square will be given in the terms to that of the IRMS. So here this I square RT will be obtained to that of same resistance and the same time sequences. So by definition in terms of the RMS value will be equal to 0.24 into 10 to the power minus 3 into RT I1 square plus I2 square till In square divided by n. So simplifyingly the I term will be equal to I1 square plus I2 square till In square divided by n to the top of 1 by 2. So so current produced, the IRMS, the will be equal to square root of this root mean squares. So I1 square plus I2 square till In square divided by n. So IRMS value will be tells us that the square root of the mean values of the sum of the squares of the current components. Here this I1, I2, I3 till In were the current components. So intervals obtained like this. These are the current component I1, I2, I3. So till In we have mentioned these are the terms explained to the top the current components. So with respect to the top current components, I is equal to root of I1 square plus I2 square and till In square divided by n. So now there will be an alternating analytical method in order to get obtained over this RMS value for the sinusoidal current. So let us consider these equations. Small I is equal to Im sin omega t. So in our previous video lecture we also mentioned over here in EMI, so electromagnetic induction video, we have discussed that this omega t will be represented in terms to the top the theta. So here also the same. So small I will be get changed out to Im sin theta. So applying square roots, so I square is equal to Im square sin square theta. Therefore the mean square of the AC will be in terms to the top the time period 0 to 25. So here this 0 to 25 will tells us one complete cycle. So 0 to 25. So 0 to 25 will be the time interval durations. After applying the time interval duration, the mean square of an AC square with respect to the analytical method, we got the value as Im square divided by 2. So this will be obtained with respect to the top the analytical method. So in terms to the top the current components, we got the equation as this I is equal to I is root of I square I1 square in terms of this obtained with respect to the top of current component, whereas with respect to the top the analytical method we got the value as Im square divided by 2. Let this RMS value IRMS value will be equal to the top 0.707 Im. So it is obtained with respect to the top the analytical equation obtained Im square divided by 2. Here this 2 and the square values get be removed. So this term and this term will produce the value as a 0.707 into Im. So IRMS value will be equal to 0.707 Im. It is obtained with respect to the top the analytical method. Okay. So in that analytical method we are going to get find over the voltage produced, alternating voltage with respect to that of IRMS. So this IRMS will be obtained with respect to the analytical method. We got the value as 0.707 Im. So now we are going to get the value regarding to the top VRMS, the voltage. So the VRMS will be obtained with respect to the top Vm square divided by 2. So again we are going to with respect to this root and divided denominator 2 and square gives the value 0.707 Vm. So VRMS value will be equal to 0.707 Vm. So and finally we are going to say that the RMS value will be equal to the top the root of area under the square curve of one cycle divided by the period. Here this period is like this term t. So the area under the square curve. So here this area under the square curve means from this to this. Here this says is about to the top the area and the period. So period means the time period. So time period here we are mentioning with respect to time. So time variant. So the time may be get start from 0 to 2 pi. So with respect to the top that 0 to 2 pi, the time period will be get reflected. For one square it will be get conquer over some area. So that is the thing mentioned over here, that the normally RMS value will be equal to root of area under the square curve of one cycle divided by period. Analytically we got the value for the IRMS value is equal to Im square divided by 2, which will be equal to 0.707 Im. For us VRMS we got the value as a 0.707 Vm. Okay, now we are going to discuss to the another topic called as the average value of the AC. Here this the average value of the AC is obtained with respect to the steady current which transfer what the across the circuit with the same charge will be transferred by AC across the same circuit in all the same time, which means that normally it has some average value. Let us consider this is the time period. So 0 to pi is a time period. For the 0 to time period it will be have some constant energy value, whereas which means that there will be some constant value energy is obtained all over there, which means that for an example we are going to consider the phi as a value. Here this phi will be greater only, not below to that of the phi. This is the common value. Phi will be obtaining in all the parts. Here it may be obtained 6, 7, 8, 10, 11, 12. So all this term we are going, if suppose the value we are going to get considered phi is get completed over here, means all the time period from 0 to pi the charges will be get occur. So this is the term they have mentioned here, the average value of an AC given by a steady current which transfers across a circuit in the same charge, which means the same energy as it will be transferring by across the AC to the same circuit in the same time. Okay, so now determining this average value, the equation is going to be mentioned like this. So the average value of the current IAV is equal to I1 plus I2 till IN divided by N. So I1, I2, IN are the current components. So these current components will give the average value of the current. So with respect to terms of a short time interval 0 to t time interval, the equation is going to be changed over like this in terms of the integrating and differentiating parts as. So 1 divided by t time interval of 0 to t I dt. So this with respect to this ratio of the area under the curve over one complete cycle is to be the base. So with respect to this we have got the value regarding to the IAV is equal to 1 divided by t integrating part time interval 0 to t I into dt. Now the average value for this symmetrical and the non-symmetrical waves is we are going to discuss here. In case suppose if we are having a symmetrical alternating current and the voltage wave, there exists some two exact similar half cycles, as whether it is maybe a sinusoidal or it may be a non-sinusoidal wave. In such cases the average value over a complete cycle will be equal to 0. Let us I am saying again, if suppose now we are going to get considering this symmetrical alternating current or any voltages wave, there will be existing the similar half waves, as whether if we are going to get consider sinusoidal or non-sinusoidal wave. At that condition the average value over a complete cycle will be equal to 0. So that only this symmetrical wave has the average value is taken from for only one half cycle. So that only we are going to consider over this a half cycle only, not for a complete cycle. If we are going to get one complete cycle, means we are going to get the value as a 0. If for suppose we are taking for one half cycle, means it has give some results to that of some numbers for that of average value. In the case of the suppose in the case to that of the unsymmetrical way, whereas in the symmetrical way you are going to get consider over one half cycle only, not a complete cycle. Whereas in that unsymmetrical way it is directly opposite, like that we are going to get considered over the whole cycle only, not a half cycle. This is the different in terms as compared to that of the average value of the symmetrical and unsymmetrical wave. So the now we are going to get to involve to the analytical method for the average value of the sinusoidal current. So now we are going to get consider over this equation, small I is equal to Im sin theta. So here this theta maybe gives the value to that of omega t. So with respect to the top the equation I average value with this equation, now we are going to get change over the conditions with respect to the top time interval 0 to pi. There it may be considered the time interval as 0 to t. Now we are going to get considered the time interval as a t, and 1 divided by 5, 0 to 5 Im sin omega t will respect to the top d sin theta into d theta. So now the value get be changed over like this, 0.637 into Im. So this value will be equal to that of the average current obtained with respect to that of the analytical method. Now for the voltage across the alternating voltage, which means that the average voltage obtained across a sinusoidal current with respect to that of a voltage, we are going to get the value as similar to that of that 0.637 Vm. So average voltage VAV is equal to 0.637 Vm, whereas the average value for a current will also gives the same value, 0.637 Im. So these are the things that will be get obtained over from with respect to the analytical method. So now the next thing we are going to get discussed in this average value of the AC is the two terms such as the form factor and the peak factor. So this peak factor is also can be tell to the cost factor. So this form and peak factor get be related to the common thing is the RMS value, which means that with respect to the RMS value, this form and peak factor will be get obtained. So let us for an example, for a sinusoidal wave, the form factor Kf will be equal to the RMS value of the sinusoidal wave and to that of the average value. So normally we have the two values. So RMS value for the sinusoidal wave, we got the value as a 0.707 Vm, and with respect to that of the average value of the current or voltage we have got in the previous terms. So this term and this term is an average, and to that before to that of RMS we also got the values like this. So these values we are going to get substitute over in the final equation, form factor and the peak factor. So the form factor will gives the value as a 1.11. So the form factor for a sinusoidal wave, so Kf is equal to 1.11, whereas the peak factor gives us the value as a 1.414. This is the, let us for an blindly we can say for a sinusoidal wave the form factor will gives the value as a 1.11, whereas for the peak factor for the sinusoidal wave we are going to say that the value will be equal to the of 1.414. This peak factor will be obtained with respect to the peak value and to that of RMS value. RMS value we have this part, so this root 2 will go upwards, so that only we got this value. So Vm will get cancelled over there, so the root 2 value, analytical value, will be 1.414. So these are the things that get covered over this form and peak factor. So the common thing is the RMS value. Thank you.